All right, so centripetal force, this sort of looks at some of the things we talked about yesterday in that quiz, so it's going to explain them a little bit better. 13.3 centripetal force. If you whirl a tin can on the end of a string, you find that you must keep pulling on the string. You pull inward on the string to keep the can revolving over your head in a circular path. A force of some kind is required for any kind of circular motion. Any force that causes an object to follow a circular path is called a centripetal force. You should highlight that. Any force that causes an object to follow a circular path is called a centripetal force. What is centripetal? Means center seeking or toward the center. The force that holds the occupant safely in the rotating carnival ride, figure 13.1, which I don't think we see here, but you know what's it called there at the fair every year? The G-force thing, where you stand up. Have you ever noticed they got that little rinky-dinky rope thing that you stand in there and there's that?
That's just like a front kind of thing.
Exactly.
You feel safe.
That's going to save you. It's like quarter-inch rope.
And where
if anything, it would cut you in two.
Why would you fall forwards if the force takes you out?
Does the force take you out, or is the force in? We're talking about that, that at the fair, right? You get in, it's that big giant circle, right? You go in, you stand in there, right? Everyone faces into the circle, right? They put that little rope across, right? And then it starts going around like this, and then it starts sort of like angling, right?
Oh, yeah.
Right? Well, that little rope thing, he doesn't do nothing. What's it there for?
To make you feel...
Actually, about all it does, it might keep you in at the start, right? Like there might be some sudden movement at the start that you might fall forward kind of. But really, you could do it without the change, right? Absolutely.
So how I like climbing up there. Trying to stand up like on your knees, like like that.
That thing,
Get over the top and it just whips you out.
That thing scares me.
I don't try to climb it out.
Without the force, the motion of the occupants would be along a straight line and they would not revolve. Centripetal force is not a new kind of force. It is simply the name given to any force that is directed at right angles to the path of a moving object and tends to produce circular motion. Okay, let's highlight that one as well. So it's any force that is directed at right angles to the path. Okay? So it's a force that's perpendicular to the velocity. Gravitational force directed toward the center of the Earth holds the moon in an almost circular orbit about the Earth. Electrons that revolve around the nucleus of an atom are held by an electrical force that is directed toward the central nucleus. Centripetal force plays the main role in the operation of a centrifuge. A familiar example is the spinning tub in an automatic washing machine. Are any of you gentlemen familiar with the washing machine in your basement? As I expected, none of you. Little joke. You know where it is. You know that Mom takes stuff down there and it comes back clean. Yeah. Fair enough. You might be familiar with the salad spinner in the kitchen. You know that thing? Okay, same idea, right? Centrifuge that someone might work in a blood laboratory would be the same idea. So, in its spin cycle, the tub rotates at high speed. The tub's inner wall exerts a centripetal force on the wet clothes, which are forced into a circular path. The tub exerts great force on the clothes, but the holes in the tub prevent the tub from exerting the same force on the water in the clothes. The water therefore escapes. It's important to note that a force acts on the clothes, not the water. Right? No force causes the water to fly out. The water will do that anyway, as it tends to move by inertia in a straight line path, Newton's first law, unless acted upon by a centripetal or other force. So interesting enough, the clothes are forced away from the water, not the other way around. When an automobile rounds a corner, the sideways friction between the tires and the road provides a centripetal force that holds the car in a curved path. If the force of friction is not great enough, the car fails to make the curve and the tires slide sideways and the car skids. So as I pointed out yesterday, it's actually friction that forces you around the corner as you make that left turn.
So I see.
No friction, you can't make the corner, right?
And then I fall in a snowbank.
Yeah.
Yeah.
So what's up with centripetal and centrifugal forces? In the preceding example, circular motion was described as caused by a center-directed force. Sometimes an outward force is attributed to circular motion. This outward force is called centrifugal or centrifugal. Centrifugal means center fleeing or away from the center. In the case of the whirling can, it's a common misconception to state that a centrifugal force pulls outward on the can. Is that true? Is there an outward force on the can?
No.
Of course not. What would be providing it? What would be pushing the can outward?
You blow on
Can't
it.
push on the string.
You gotta blow on it while you're throwing it.
That's so weird though, because like it feels like like when you get swung around like that, like
Yeah, yeah. But that's not, it's inertia, right? Do you feel like there's a force on you? Absolutely. It's a force that's pushing you toward the center, right? That's the force you feel, right? But you feel it outwards because of inertia. It's no different than going around a corner in a car, right? If you went around a corner fast, you feel like you're going outside. If the string holding the whirling can breaks, it's commonly stated that a centrifugal force pulls the can from its circular path. Not true. The fact is that when the string breaks, the can goes off in a tangent straight line path because no force acts on it, right? Because an object in motion stays in motion. We illustrate this further with another example. Suppose you are the passenger of a car that suddenly stops short. You pitch forward against the dashboard. Stop short means like they slam on the brakes, right? You all go forward, crack your head on the dash. When this happens, you don't say that something forced you forward. You know that you pitched forward because of the absence of a force, which is what a seatbelt would have provided. Similarly, if you're in a car that rounds a sharp corner to the left, you tend to pitch outward to the right. Not because of some outward or centrifugal force, but because there is no centripetal force holding you in circular motion as a seatbelt would provide. The idea that a centrifugal force bangs you against the car door is a misconception. So when you swing a tin can in a circular path, there is no force pulling the can outward. Only the pull by the string acts on the can and pulls the can inward. The outward force is on the string. Is that true? Is there in a circular, if the string is here, right, and there's a rubber stopper or whatever you have on the end, is there an outward force on the string? Yep. Right? That rubber stopper, because of inertia, is doing what? It's pulling that string outward. That is certainly true. But is there a force on the rubber stopper or the can? Only inward. Kind of weird. The acceleration is in, as is the force. The force and acceleration have to be in the same direction.
Yeah.
And that force is called centripetal force because it's in... Oh, okay, this is, yeah. Like if there was this, right, that would be instantaneous velocity. The whole thing happens, as I pointed out yesterday with my drawing, is when the velocity and the acceleration are 90 degrees to each other, you get a circular path. Now, it may not complete that circular path, like when you're launching a bullet or something or other, right? But the path is circular. All right, so the outward force is on the string, but not on the can. Now, suppose there's a ladybug inside the whirling can, or Sean on the ride at the fair. The can presses against the bug's feet and provides the centripetal force that holds it in a circular path. The ladybug, in turn, presses against the floor of the can, but neglecting gravity, the only force exerted on a ladybug is the force of the can on its feet. From our outside stationary frame of reference, so as a human outside the moving object, we see that there is no centrifugal force exerted on a ladybug. We can't describe, we can't see, we can't model a outward force of a ladybug. Just as there is no centrifugal force exerted on the person who lurched against the car door. The centrifugal force effect, in quotations, is attributed not to any real force, but to inertia. The tendency of the moving body to follow a straight line path. Try telling that to the ladybug's going to say, there's a big force on it. That guy felt 6 G's of force. Right? So we feel the outside force, but it's really not a force, it's really what? Sort of, it's inertia. Right? It's the tendency of us to try to go in a straight line path, but there is an inward force on us that's not allowing that.
Is this all the same for when like there is no string? Like it's just like put something in a tire kind of thing, you roll it?
It's the force of the tire pushing it in, right? Or like the car, they went around the loop, right? There was no string, but the car was moving, that's true. There's a force propelling it forward. But it wants to go in a straight line, and the road pushes it towards the center, just because of the the path. Yeah, it's kind of confusing. There's no doubt about it.
Stop recording here.
Stop here. Okay, so the centrifugal force in a rotating reference frame. Our view of nature is very much influenced by the frame of reference from which we view it. And this goes right back to almost like the first week of grade 11, frame of reference. When we sit on the seat of a fast-moving train, we have no speed at all relative to the train, but an appreciable speed relative to the reference frame of the stationary ground side. If I'm sitting across the aisle from Sean on a train, I look over, he's not moving, he's just sitting there, right beside me, right? But Mike, he's standing outside on the ground, he sees us, go flying past, right? Our frame of reference is different. We have no speed at all relative to the train, but an appreciable speed relative to the reference frame of the stationary ground outside. We have just seen that in a non-rotating reference frame, the force that holds an object in circular motion is a centripetal force. For the ladybug, the bottom of the can exerts a force on its feet. No other force is acting on the ladybug. Right? Now, there's this whole, I thought there was equal and opposite forces. If I push on the filing cabinet, right, the filing cabinet pushes on me. There has to be an equal and opposite force. How can they say that there's only one force acting on the ladybug? What's going on here? You're on the right track, right? It's a little play of words, a little trick of words that people really don't understand. When I say I push on the filing cabinet pushes back on me, how many objects are we talking about here? 2. I force on the filing cabinet force on me, right? How many forces are on me when I lean against the filing cabinet? Only one, right? Only one, well, except for gravity. It's only one sideways force, right? So the same thing with the ladybug. It's that force inward, right? You can't say, well, there's a missing force, because is there a force of the ladybug on the can? Yes, there is. That exists, right? Okay. It's kind of confusing. You'll have to sort of stop and think about it. It's taken me a while to be able to sort of work through that explanation. Nature seen from the reference frame of the rotating system is different. In other words, if you're in the can, things are different. In the rotating frame, in addition to the force of the can on ladybug's feet, there is a centrifugal force that is exerted on the ladybug. So in other words, this centrifugal force really only exists for people that are in the can, or ladybugs, or whatever they are. Centrifugal force in a rotating reference frame is a force in its own right, as real as the pull of gravity. However, there is a fundamental difference. Gravitational force is an interaction between one mass and another. The gravity we experience is our interaction with the Earth. But centrifugal force in the rotating frame is not part of an interaction. It is like gravity, but with nothing pulling. Nothing produces it. It is the result of rotation. There's no object that produces it. For this reason, physicists rank it as a fictitious force and not a real force like gravity, electromagnetism, and nuclear forces. Nevertheless, to observers who are in a rotating system, centrifugal force seems to be, and is interpreted to be, a very real force. Just as from the surface of the Earth we find gravity ever present, so within a rotating system, centrifugal force is ever present. It's there. You might have to read this again to really sort of get it. Okay, here's 2 questions. Did I make them? Oh, I thought I made them in the clickers. I did not. Here's 2 questions I want you to read. Talk amongst yourself a few minutes, and then I'll give you an answer. Mike doesn't like the words in the bottom.
Yeah, wait.
So, a heavy iron ball is attached by a spring to a rotating platform known as a merry-go-round, as shown in the sketch. 2 observers, one in the rotating frame, that's the man, and one on the ground at rest, that's the woman, observe its motion. Which observer sees the ball being pulled outward, stretching the spring?
The guy at the bottom on the rotating thing will see it go out.
Yeah, so does he see it being pulled outward?
Yeah.
Pulled inward, or
No, he'll see it pulled out.
Yeah, exactly, right? The man is the first one. Which observer sees the ball being pulled outward? The man, right? Which sees the spring pulling the ball in a circle? The woman. Outside, right? She sees the ball going in a circle. What does he see? He's just sitting there. Well, someone's pulling the ball in the spring. Am I moving? Is the ball moving? Right? He's in the reference frame. Just as you and I are on the Earth, we are rotating right now. Do I see you guys moving? No. If I was way out in space, right? Hanging out there, would I see you rotating beneath me? Yeah?
Yeah.
But really, you're
Do
doing
not
what?
see me rotate.
Well, I'd have to have really good vision.
Here.
Okay, now here's an even more of a brain teaser. The spring in the sketch is observed to stretch 10 centimeters when the ball is midway between the rotational axis and the outer edge of the circular platform. In other words, this distance here is 10. If the spring support is moved, if I take this post, okay, and this is kind of hard to explain here. Let me see if I can redraw it. I should probably do this every year. Okay, that's 10 centimeters, and there's the ball, right? Now if I redraw my thing, and I move the post out here, so it's no longer at the center, right? Where will the ball go? Will it go 10 centimeters, or will it go farther?
Farther.
There's a greater.
There's greater acceleration required to move it when it's farther.
So, will the spring stretch farther?
No, it's the same.
Yes.
It's the same.
Same distance, Mike?
I think it's the same.
You know what? I always have a hard time explaining this, so I'm going to look at the words below.
No, you can't look at the words below.
Why not?
It's not confusing.
Oh, I thought maybe I could just rotate this. Oh yeah, we got to watch helium balloon in a car. Okay, I'm going to have to get my sheet because I always forget how to explain
The
this.
ball will have twice the linear speed at twice distance.
Yeah, the ball will have twice the linear speed. What does that mean?
It'll be twice as
It's
fast
moving faster. Why does it have to move faster?
to keep it up
Because it's got to go
further.
farther around in the same amount of time. So it's got a greater linear speed at twice the distance. The greater the speed, the greater will be the centripetal or centrifugal force, which will also be twice in strength of the spring, 20 centimeters. So this will not be 10. This, in fact, here will be, it'll be like this. It'll be 20. Okay? Farther out. The rest frame observer, that's the man. Oh no, sorry, I'm reading the wrong here, right? We see in chapter 18 that the stretch of a spring is directly proportional to the applied force. And we haven't done Hooke's law yet. No, we haven't done any spring stuff, have we? No, that's coming up. We might get to it. After this stuff, we're going to do work and energy. Okay. How come when you slam on the brakes, if I got a tennis ball, the tennis ball goes boom off the windshield, but the helium balloon goes backwards? What is up with that?
Why? Because like the string attached to it or something has something to do with it? Has anything to do with the string?
Nope, nothing actually. Just hold it in place.
Yo, the centrifugal force is.
If it was a regular balloon, what would happen? It would do the same thing that the tennis ball would do.
Force is.
But why does a helium balloon do the opposite?
It's lighter in the air.
It is lighter in air, so what happens?
Air around it is being pushed to the side.
You're on the right track, right? There's my car,
That's a nice looking car.
poorly drawn, right? And when I slam on the brakes, the tennis ball and everyone inside it, including the air, goes where? Forward. All of the air in the cab moves to the front of the car, right? Because actually what's happening is the air is still in the car is being pushed along, right? The car stops, everything inside goes forward, so at the front of the car you have this region of really dense air which forces the balloon backward.
Because it's so much lighter.
So much lighter. That's why. It's kind of cool, really. One of these years, some kid's going to show me actual video that they have made of this, but no one has ever taken me up on it.